Roger Penrose's Conformal Cyclic Cosmology proposes that the remote future of one universe can be conformally matched to the Big Bang of the next, and claims the cosmic microwave background may preserve the debris. You have lived this exact life trillions of times before. That is the provocative claim we will examine today. The Bekenstein Bound places an upper limit on how much information can exist in a bounded region of space. The Quantum Recurrence Theorem, proven in 1957, demonstrates that under certain conditions, any quantum system must eventually return arbitrarily close to its initial state. Hawking points, claimed hotspots in the CMB 3 to 4 degrees across, are presented as fossil signatures of black holes from a previous aeon. And the Planck satellite has mapped the cosmic microwave background at 5 arc-minute resolution, providing the data on which these claims are tested. What follows is an examination of the evidence for and against. By the end, you will understand why the claim in this video's title is not settled science, but a conditional argument that depends on assumptions physics has not yet resolved. You will understand the Bekenstein Bound and what it says about finite information. You will understand the Quantum Recurrence Theorem and the conditions under which it applies. You will understand Roger Penrose's Conformal Cyclic Cosmology, the Nobel laureate's proposal that the universe cycles through infinite aeons, and the contested observational evidence claimed to support it. You will understand the Boltzmann brain problem and why naive recurrence arguments lead to paradox. And you will understand with precision which premises in the recurrence argument are supported, which are conditional and which are unknown. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us begin with what is actually being claimed. The title of this video, "You Have Lived This Exact Life Trillions of Times Before," is not a statement I am making as fact. It follows from a chain of premises, each requiring examination. Each premise is conditional, and the chain is only as strong as its weakest link. The question is not whether the claim is provocative, it is, but whether the premises that would make it true are themselves true. The argument reconstructed. First premise: the amount of information that can exist in a bounded region of space is finite, not infinite. This is the Bekenstein Bound, proposed by Jacob Bekenstein in 1981. Second premise: if information is finite, then the number of possible configurations, the number of possible microstates, is also finite. This follows from the relationship between entropy and state counting. N scales like e to the s over k, where n is the number of microstates and s is entropy. Third premise: if the number of possible configurations is finite, and if time extends long enough, then every configuration must eventually recur. This is the Quantum Recurrence Theorem, proven by Bochieri and Loinger in 1957 as a quantum analog of the classical Poincaré recurrence theorem from 1890. Fourth premise: if configurations recur, and if you are a configuration, a specific arrangement of atoms, a specific pattern of information, then you must eventually recur. Fifth premise: if you recur and if time is infinite, or the universe cycles eternally, then you have already recurred. Not once, trillions of times. More. That is the argument. It is logically valid, the conclusion follows from the premises. Logical validity is not the same as truth. The question is whether the premises are true, and that is where the investigation begins. I will examine each premise in turn. I will present the evidence for it. I will present the challenges to it, and I will be precise about where physics provides answers and where it does not. This is the part that stays with me, not because the conclusion is comforting or terrifying, but because the conditional nature of the argument is so often obscured. The claim, "You have lived this life before," is presented as a revelation. What is rarely presented is the list of assumptions required to make it true, and the fact that several of those assumptions are contested, unresolved, or dependent on physics we do not yet have. Let us begin with the first premise, the Bekenstein Bound. In 1981, theoretical physicist Jacob Bekenstein proposed an upper limit on the entropy and the information content that can be contained in a region of space. This was not an arbitrary mathematical bound, but emerged from careful analysis of black hole thermodynamics, from the realization that black holes have maximum entropy for their size, and from the generalization of that insight to arbitrary systems. The bound in its common form is S is less than or equal to 2 pi k(E)r over h bar c. S is entropy, a measure of the number of possible arrangements of a system that appear macroscopically identical. K is the Boltzmann constant, approximately 1.38 times 10 to the negative 23 joules per Kelvin. E is the total energy in the region. R is the radius of the region. H bar is the reduced Planck constant, approximately 1.05 times 10 to the negative 34 joule seconds. And c is the speed of light, approximately 3 times 10 to the 8 meters per second. What this equation states is direct. For a given amount of energy contained in a sphere of a given radius, there exists a maximum amount of entropy and a maximum amount of information that can fit. The bound is finite, not infinite, finite. This matters because information, in physics, relates to the number of distinguishable states a system can occupy. If entropy is capped, then the number of possible microstates is capped. The relationship is n scales like e to the s over k. If s has a maximum value, then n has a maximum value. The system can only occupy a finite number of configurations. For this script, the conceptual leap is worth stating explicitly. Bits scale linearly with entropy, but states scale exponentially with entropy. Even a finite information bound can correspond to an incomprehensibly large number of states. The word finite can mislead, suggesting smallness, boundedness in a comprehensible way. Finite does not mean small. Finite means bounded, but the bound can be so large that finite becomes, for all practical purposes, indistinguishable from infinite. This distinction will matter when we reach the recurrence argument. Consider the observable universe. If you apply a naive entropy bound to the observable universe, the resulting number of possible states is often estimated at something like e to the power of 10 to the 120. That is not a number you can write down. That is not a number you can comprehend. That is a number so large that finite becomes almost meaningless as a practical constraint, except over timescales so vast that they too become incomprehensible. The Bekenstein bound, as stated, is not without complications. A modern review by physicist Don Page surveys both the supporting arguments for the Bekenstein bound and the counterexamples that arise under naive definitions. The bound's validity depends strongly on how entropy and system size are defined in quantum field theory. Naive definitions can violate the bound. Rigorous definitions, such as those developed by theoretical physicist Horacio Cassini using relative entropy, can put at least some forms of the bound on solid mathematical footing. For cosmology specifically, the Bekenstein bound, as stated, may not be the relevant constraint. In gravitating systems and in expanding spacetimes, naive entropy in a volume bounds can fail. The more appropriate bound is often the covariant entropy bound, proposed by theoretical physicist Raphael Bousso in 1999. The covariant entropy bound argues that entropy flowing through appropriate light sheets, surfaces traced by light rays, is bounded by area in Planck units. Later work, including contributions by Juan Maldacena, has proven quantum versions of this bound under specified conditions. The practical meaning for this investigation, the most defensible, finite information claims in cosmology are usually tied to horizons and areas, not arbitrary coordinate volumes. The de Sitter horizon, the cosmological horizon in a universe with a positive cosmological constant, like ours appears to have, possesses a finite area. That finite area implies a finite entropy, and that finite entropy implies a finite number of accessible states within the horizon. The de Sitter entropy is given by S equals Ka over 4 Lp squared. A is the horizon area. Lp is the Planck length, approximately 1.6 times 10 to the negative 35 meters. This is the same area-entropy relationship that applies to black holes, first derived by Jacob Bekenstein and Stephen Hawking in the 1970s. If the universe has a positive cosmological constant, if it will expand forever, approaching a de Sitter state, then there is a horizon. That horizon has a finite area. That finite area implies a finite entropy, and that finite entropy implies a finite number of microstates accessible to an observer within the horizon. This is the foundation of the finite information premise. It is not speculative. It is grounded in some of the most robust results in theoretical physics, black hole thermodynamics, the Bekenstein bound, the covariant entropy bound, the area entropy law. Finite is not the same as small, and finite information is not the same as guaranteed repetition. Before proceeding, I want to ground this in something concrete. The entropy bound is not an abstract mathematical curiosity. It has physical implications that have been tested, at least in the black hole case. When Stephen Hawking, building on Bekenstein's work, derived that black holes have entropy proportional to their horizon area, the result was initially met with skepticism. How could a black hole, classically a one-way membrane from which nothing escapes, have entropy? Entropy is a count of microstates. What are the microstates of a black hole? The answer came from string theory. In 1996, Andrew Strominger and Kumran Vafa calculated the entropy of certain supersymmetric black holes using string-theoretic methods, and found exact agreement with the Bekenstein-Hawking area formula. This was not a fit with adjustable parameters. It was a direct calculation that matched a completely independent prediction. This is one of the strongest pieces of evidence that the area entropy law is physically real, that horizons really do correspond to finite information, that the bound is not just a mathematical inequality, but a description of actual physics. The de Sitter horizon, the cosmological horizon in our universe, with its positive cosmological constant, is analogous but distinct. It is a horizon for observers, not for objects falling in. The thermodynamic treatment, developed by Gary Gibbons and Stephen Hawking in 1977, suggests it too has finite entropy. And if our universe approaches a de Sitter state in the far future, as current observations suggest, then our entire causal patch may have a finite information capacity. The number is vast, it is finite, and that finiteness is the first link in the chain. Let me now examine the second step in the chain. From finite information to finite states. The relationship between entropy and state counting is n scales like e to the s over k. This is standard statistical mechanics. If you know the entropy of a system, you know, roughly, how many microstates are compatible with that macroscopic description. For the de Sitter horizon, the entropy is enormous. Using the cosmological parameters measured by the Planck satellite, a Hubble constant of approximately 67.4 kilometers per second per megaparsec, implying a Hubble radius of roughly 14.4 billion light-years, or about 1.4 times 10 to the 26 meters, the horizon area is on the order of 10 to the 53 square meters. Divided by the Planck area of about 2.6 times 10 to the negative 70 square meters, this gives an entropy of order 10 to the 122 in natural units. The number of microstates is then e to the power of 10 to the 122. This is finite. This is also a number so large that no analogy can capture it. It exceeds the number of atoms in the observable universe raised to any power you can write down. It exceeds the number of Planck times that have elapsed since the Big Bang raised to any power you can write down. It is finite in the mathematical sense. It is infinite in the practical sense. For the recurrence argument, finite is what matters. Because if the number of states is finite, and if the system evolves through those states according to dynamics that preserve certain mathematical properties, then recurrence is not just possible. It is guaranteed. This brings us to the third premise, the Quantum Recurrence Theorem. In 1957, physicists Bocchieri and Loinger published a paper presenting a quantum analog of the classical Poincaré recurrence theorem. The classical theorem, formulated by mathematician Henri Poincaré in 1890, states that for a system with a bounded phase space evolving under measure-preserving dynamics, almost every initial state will eventually return arbitrarily close to itself. The quantum version makes a similar claim. For a suitable closed quantum system, the system's state will return arbitrarily close to its initial state after sufficiently long time. The condition is stated as the norm of psi at time t minus psi at time 0 is less than epsilon. For any epsilon greater than 0, any degree of closeness you specify, there exists a time t after which the system returns within that closeness of its initial state. This is clean mathematics. It is proven. It is not a speculation. Under the conditions of the theorem, recurrence is guaranteed. The conditions matter. The quantum recurrence theorem applies to closed quantum systems with a discrete spectrum, systems where the energy levels are quantized and countable. It does not automatically apply to open systems, to systems with continuous spectra, or to systems whose dynamics violate the assumptions of the theorem. And here is where cosmology introduces complications. Is the universe, or the relevant causal patch within a de Sitter horizon, a closed system with a discrete spectrum? This is not a settled question. Modern quantum gravity does not yet supply a universally accepted operational definition of the Hilbert space of the universe's causal patch, with known dynamics for timescales comparable to recurrence times. The bound on states the finite entropy suggests finiteness. The dynamical structure required for the recurrence theorem to apply is not guaranteed by the entropy bound alone. Papers discussing recurrence in de Sitter-like settings, including work by Lisa Dyson, Matthew Kleben, and Leonard Susskind, frame recurrences as ultra-long-time phenomena with paradox implications. They note that if the universe really does approach a de Sitter state with finite entropy, then Poincaré recurrence should eventually occur. But the timescale is so vast and the intermediate dynamics so uncertain that the conclusion is more of a logical extrapolation than an observable prediction. Think about that number. Let it settle. The recurrence time scales like e to the s. If s is 10 to the 122, then the recurrence time is e to the 10 to the 122 Planck times. A Planck time is about 5.4 times 10 to the negative 44 seconds. The age of the universe is about 4.3 times 10 to the 17 seconds, roughly 10 to the 60 Planck times. The recurrence time is not 10 to the 60 Planck times. It is not 10 to the 100 Planck times. It is e to the 10 to the 122 Planck times. A number so large that the number of digits in the number of digits in the number has more digits than atoms in the observable universe. Let me try to make this concrete, because abstract numbers lose their impact. The number of atoms in the observable universe is roughly 10 to the 80. That is a 1 followed by 80 zeros. It is already beyond ordinary comprehension. No human has ever counted to 10 to the 80. No human ever will. It is finite. It can be written. 10 to the 122 is vastly larger. It is 10 to the 80 multiplied by 10 to the 42. It is the number of atoms in the universe times a trillion, 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 trillion. Still writable, 1 followed by 122 zeros. E to the 10 to the 122 is not writable. The exponent alone, 10 to the 122, has 123 digits. The number e to that power has 10 to the 122 digits. You cannot write it, you cannot store it, you cannot represent it in any physical medium in the observable universe, because the number of atoms in the observable universe is only 10 to the 80, and you need 10 to the 122 digits. This is the recurrence time. Not years, not Planck times, just the number itself before you even ask what units it is in. And if time is truly infinite, this number is reached, and surpassed, and reached again. Finitude multiplied by infinity gives infinity. The recurrence time is finite. Time, in the assumption, is infinite. Recurrence occurs, not once, infinitely many times. The mathematics is correct. The intuition fails. We are not equipped to comprehend durations of this magnitude. We can write the symbols. We can verify the logic. We cannot feel what they mean. Perhaps that is the deepest limitation. Not a limitation of physics, but of psychology. We developed comprehension for timescales relevant to survival. Seconds, days, seasons, lifetimes, maybe a few generations. We did not develop comprehension for e to the 10 to the 122 Planck times. The concept exists, the comprehension does not. Finite, effectively infinite for any practical purpose. And if time is truly infinite, if the universe persists forever, if no terminal cutoffs occur, then even this incomprehensible timescale is eventually reached, and then surpassed, and then reached again, trillions of times more. This is the logical structure of the recurrence argument. It does not depend on the number being small. It depends only on the number being finite and time being infinite. Is time infinite? This brings us to the fourth complication. The assumption that time extends infinitely into the future is itself conditional. Several mechanisms could truncate the future. Vacuum decay. If the current vacuum state is metastable, not the true ground state, then a transition to the true vacuum could occur, destroying all existing structures. This is a known possibility in particle physics, though the timescale is uncertain and may be vastly longer than the current age of the universe. Phase transitions. Changes in the fundamental structure of space-time or matter could occur at extreme timescales, altering the dynamics in ways that prevent recurrence. The end of space-time itself. Some models of quantum gravity suggest that space-time may not persist indefinitely, that it may have a finite lifespan in some fundamental sense. These are uncertainties, not certainties. They are uncertainties that the recurrence argument must assume away. The argument requires that time extends long enough for recurrence to occur. If time is cut off before the recurrence timescale, which is again e to the 10 to the 122 Planck times, then recurrence does not happen. This is where science describes the bounding logic but does not deliver a guarantee. We can calculate what would happen if the universe persists forever. We cannot prove that it will. Now let me examine the fifth step, from recurrence to U. Even granting that the system recurs, that the overall quantum state of the causal patch returns arbitrarily close to some prior state, the claim "you have lived this exact life before" requires a stronger statement. It requires that your specific configuration, the specific arrangement of atoms that constitutes you, the specific pattern of information that constitutes your memories, the specific microstate that corresponds to your existence at this moment, recurs. This is logically stronger than recurrence somewhere in the state space. The recurrence theorem guarantees return to the vicinity of the initial state. The initial state here is the state of the entire causal patch, not specifically the state of U. Whether your particular configuration recurs depends on the measure, the probability distribution, over the space of microstates. If the dynamics are ergodic, if the system eventually visits all accessible microstates with appropriate frequency, then your configuration recurs. Ergodicity is an assumption, not a proven property of de Sitter cosmology. And even if ergodicity holds, the recurrence of your specific configuration might require timescales even longer than the general recurrence time, depending on how rare your configuration is among all possible configurations. There is also a conceptual question. What counts as the same life? The physics bounds constrain microstates. The narrative claim requires that a specific microstate, your exact configuration, recurs. Microstates are defined at the level of fundamental physics. Whether two microstates that are close in the state space correspond to the same life in any meaningful sense is a question physics does not answer. Let me dwell on this because it is often glossed over in recurrence arguments. A microstate is a complete specification of all the physical degrees of freedom in a system. For you, right now, that would include the position and momentum of every particle in your body, roughly 10 to the 28 atoms, each with multiple degrees of freedom. It would include the quantum state of every electron, every photon interacting with your cells, every neurotransmitter in your synapses. It is a specification of staggering complexity. The recurrence theorem says that the state of the system will return arbitrarily close to its initial state. Arbitrarily close is not exactly the same. How close is close enough for the recurrence to count as the same life? Consider, if one electron in one atom in one cell in your brain occupies a slightly different quantum state, is that you? If one memory differs slightly, one neural connection has a different strength, is that still your exact life? The physics cannot answer this. The physics says microstates recur to within epsilon for any epsilon greater than 0. Whether a recurrence within epsilon counts as the same depends on what you mean by same. There is also the question of time ordering. The recurrence theorem says the system returns to a state close to the initial state. It does not say the system will then evolve in the same way. Quantum mechanics is deterministic at the level of wave function evolution, but measurement outcomes introduce randomness. A recurred you might make different choices, experience different outcomes, live a different life from the same initial configuration. Some philosophers and physicists argue that identity across recurrence is meaningless, that there is no fact of the matter about whether a recurred configuration is you or just a duplicate. The question becomes metaphysical rather than physical. Physics can describe the recurrence. Physics cannot adjudicate identity. This is another conditional in the chain. The claim, "you have lived this exact life before," requires not just recurrence of microstates, but a theory of identity that makes recurrence count as the same. That theory is not provided by physics. It is a conceptual addition. I return to this point often, not for comfort, for clarity. The claim, "you have lived this exact life trillions of times before," is a chain of 5 premises. 1. Finite information in the causal patch, supported by entropy bounds, but the exact value depends on horizon structure. 2. Finite information implies finite states, supported by statistical mechanics, but the number of states is incomprehensibly large. 3. Finite states plus infinite time implies recurrence, supported by the Quantum Recurrence Theorem, but requires assumptions about the system's dynamics. 4. Time is infinite, not proven. Depends on the absence of vacuum decay, phase transitions, or other terminal cutoffs. 5. Recurrence includes your specific configuration, requires ergodicity or a similar assumption, plus a definition of what counts as you. Each premise has support. Each premise has conditions. The chain is valid. The chain is conditional. Before I continue, consider what this means. Take a moment. What I have presented so far is the abstract argument, the logical structure. Now let me turn to the observational claims. Because there is a theory, Conformal Cyclic Cosmology, that claims not only that cosmic cycles occur, but that we can see evidence of previous cycles in the cosmic microwave background. This is where the investigation becomes forensic. Conformal Cyclic Cosmology, CCC, was proposed by mathematical physicist Roger Penrose, born in 1931, winner of the 2020 Nobel Prize in Physics for his work on black hole singularities. Roger Penrose shared that prize with Andrea Ghez and Reinhard Genzel, who provided observational evidence for the supermassive black hole at the center of our galaxy. Roger Penrose's contribution differed. It was theoretical, mathematical. He proved that singularities are a generic feature of gravitational collapse, not a special case. He developed twistor theory as an alternative mathematical framework for physics. He has thought deeply about the relationship between mathematics and physical reality for over 6 decades. Conformal cyclic cosmology is not a minor speculation. It is a detailed theoretical framework developed over decades by one of the most accomplished mathematical physicists alive. Authority is not evidence, and CCC's observational claims are contested. Let me present both sides, beginning with the theoretical structure. The first public presentation of conformal cyclic cosmology came in 2006, when Roger Penrose outlined what he called an outrageous proposal at a physics conference. The language was deliberate. Roger Penrose knew the idea was speculative, and he framed it that way. The written version appeared in conference proceedings that year, laying out the mathematical structure that would be developed over the following 2 decades. The core idea builds on 3 observations. First, the early universe had extraordinarily low gravitational entropy. The CMB is uniform to 1 part in 100,000. If gravity had clumped matter significantly before the CMB was released, the entropy would have been far higher. This specialness of the initial conditions is, in Roger Penrose's view, a puzzle requiring explanation. Second, the late universe, after stars have burned out, after black holes have evaporated, after protons have perhaps decayed, will consist only of radiation, no massive particles, no rest mass, and physics without rest mass is conformally invariant. Third, conformal geometry, geometry that preserves angles but not absolute lengths, allows for mathematical operations that squash infinite regions into finite boundaries and stretch singular points into smooth surfaces. Roger Penrose's insight connects these observations. If both the very early universe, when radiation dominated and masses were negligible, and the very late universe, when only massless radiation remains, are conformally invariant, then the 2 ends might be mathematically matchable. The infinite future of one aeon could be the Big Bang of the next, not causally connected in the ordinary sense, but conformally identified. The conformal rescaling equation is G tilde sub AB equals omega squared times G sub AB. G is the space-time metric, the mathematical object that defines distances and angles. Omega is the conformal factor, a function that varies from point to point. Where omega goes to 0, distances are compressed. where omega goes to infinity, distances are stretched. The metric is transformed, but angles are preserved. In conformal cyclic cosmology, omega goes to zero as you approach the remote future of an aeon. The infinite expansion is squashed down to a finite boundary. And omega goes to infinity as you approach the Big Bang of the next aeon. The initial singularity is stretched into a smooth surface. The two boundaries are then identified as the same hypersurface, the crossover. This is mathematically well defined. Is it physically meaningful? That depends on what survives the crossover. In conformal cyclic cosmology, most information from the previous aeon is lost. The conformal matching forgets the overall scale, and with it, much of the structural information about what existed. Roger Penrose argues that certain signals can persist. Specifically, the final moments of supermassive black holes. When a black hole evaporates through Hawking radiation, it releases its mass energy. The process is slow. For a solar mass black hole, the evaporation time is about 10 to the 67 years. For supermassive black holes of billions of solar masses, the time is correspondingly longer. And in CCC's picture, galactic clusters can remain gravitationally bound as the universe expands, allowing black holes to grow by merging with each other over cosmic timescales. The 2018 Hawking Points paper by Daniel An, Krzysztof Meissner, Paweł Nurowski, and Roger Penrose mentions black holes up to 10 to the 14th solar masses, 100 trillion times the mass of the Sun, with evaporation times up to 10 to the 106th years. These are not measured quantities. They are CCC internal estimates, derived from the assumption that bound galactic clusters can persist and their black holes can grow and eventually merge into single enormous objects. When such a black hole finally evaporates, it releases energy. In the remote future of the ion, this energy is released into a universe that is almost entirely empty, exponentially expanded, incredibly dilute. The energy appears as radiation propagating outward. Now apply the conformal matching. The remote future, infinite, empty, dominated by a positive cosmological constant, is conformally squashed to a boundary. The black hole's final energy release, which occurred at a specific location and time in the old aeon, becomes a point on this boundary. On the other side of the boundary, in our aeon, this point appears as a localized source. The radiation from the evaporating black hole, transformed through the conformal matching, appears as a small hotspot in our CMB. This is the Hawking point hypothesis. The points are the locations on the crossover where prior aeon black holes met their end. The Hawking refers to the radiation mechanism that made them visible. The prediction is specific: small circular hotspots a few degrees across at random locations in the CMB. Their angular size depends on the details of the conformal matching and the epoch at which the evaporation occurred. The 2018 paper focuses on spots with angular radii between 0.03 and 0.04 radians, diameters of 3 to 4 degrees. For scale, the full moon has an apparent diameter of about half a degree. A Hawking point candidate spans 6 to 8 full moons across, not a microscopic speck, a substantial patch of sky. The 2018 paper reports finding such spots and finding them at the same sky locations in both Planck and WMAP data. This is the crux of the observational claim. WMAP and Planck are independent instruments with different noise properties, launched 8 years apart, operated by different space agencies. If the same anomalous spots appear in both maps, the probability that they are pure instrument noise is reduced. The paper quantifies this. The features are present in both maps with a claimed confidence of 99.98%. This would be highly significant, between 3 and 4 sigma, depending on assumptions. It would be evidence for physics beyond the standard cosmological model. This claimed significance has been challenged, and the challenge is serious. Conformal cyclic cosmology models cosmic history as an unending succession of aeons. Each aeon resembles a standard expanding cosmology with a positive cosmological constant. The universe expands, structures form, stars burn out, black holes evaporate, and eventually, after unimaginable timescales, only radiation remains. The universe becomes increasingly dilute, increasingly cold, increasingly empty. Here is Roger Penrose's key move. In this remote future, when all massive particles have decayed and only massless radiation remains, the physics becomes conformally invariant. Conformal invariance means that the physics is unchanged by rescaling, by multiplying all lengths by a constant factor. If only massless particles exist, there is no rest mass to set a scale. Angles remain meaningful, but absolute lengths do not. Conformal cyclic cosmology proposes that this conformally invariant remote future can be matched to a new Big Bang, that the infinite future of one aeon is conformally equivalent to the Big Bang of the next. The mathematical operation is a conformal rescaling. G tilde equals omega squared times G. The metric is multiplied by a conformal factor that squashes the infinite future down to a finite boundary and stretches the Big Bang up from a singularity to a smooth surface. In conformal cyclic cosmology, the Big Bang is not a beginning. It is a transition, a crossover from the previous aeon's remote future to our aeon's earliest moments. And the crossover, Roger Penrose argues, is not perfectly smooth. Information from the previous aeon, particularly from the final evaporation of supermassive black holes, can leak through. This is where Hawking points enter. Stephen Hawking, born in 1942, died in 2018, showed that black holes are not perfectly black. They emit radiation, Hawking radiation, due to quantum effects near the event horizon. Over vast timescales, this radiation causes black holes to lose mass and eventually evaporate entirely. In conformal cyclic cosmology, the supermassive black holes that form in galactic clusters can grow enormous. The 2018 Hawking Points paper mentions masses up to 10 to the 14th solar masses, and their evaporation can take correspondingly long times, up to 10 to the 106th years. When these black holes finally evaporate, they release their remaining energy in a final burst. The 2018 paper, authored by Daniel Ann, Christoph Meissner, Paweł Nurawski, and Roger Penrose, argues that this final burst, occurring in the remote future of the previous aeon, is compressed by the conformal matching into a point-like event on the crossover surface. On our side of the crossover, in our aeon's cosmic microwave background, this point-like event appears as a small circular hotspot, a Hawking point. The paper claims to have found these Hawking points. It reports anomalous circular spots, with angular radii between 0.03 and 0.04 radians, diameters of about 3 to 4 degrees, roughly 8 times the apparent diameter of the full moon. The paper reports finding these spots at the same sky locations in both Planck and WMAP data, two independent CMB maps with different instruments and different noise properties. The paper argues that finding the same anomalous features in both maps reduces the probability that they are pure noise. The claimed confidence level is 99.98%. This is an extraordinary claim. If true, it would be evidence for physics beyond the standard cosmological model, evidence for a previous aeon, for a cyclic universe, for Roger Penrose's conformal matching hypothesis. Extraordinary claims require extraordinary evidence, and the Hawking Point claim has been challenged. In 2020, cosmologists Dylan Zhao and Douglas Scott published a detailed re-evaluation of the Hawking Point claim. Their paper investigates the claimed 99.98% confidence and finds that after properly accounting for the search procedure, specifically after marginalizing over the range of ring sizes that were scanned, the significance drops dramatically to about 87% confidence, approximately 1 sigma. 1 sigma is not statistically significant. 1 sigma means that a result this extreme would occur by chance about 13% of the time. It is not evidence. The issue is the look elsewhere effect, also called the trials factor. When you search for a signal across many possible parameters, in this case, ring sizes from 0.03 to 0.04 radians, you are effectively performing multiple statistical tests. If you then report only the most significant result without accounting for the multiple tests, you inflate the apparent significance. This is a well-known statistical pitfall, and it is exactly what Zhao and Scott argue occurred in the Hawking Point analysis. The Zhao and Scott paper also reports finding no corresponding polarization signature in stacked Hawking Point candidates. If Hawking points were genuine physical temperature features in the CMB, they might be expected to correlate with polarization in certain models. The absence of polarization signal is not definitive. It depends on the specific model, but it is another data point against the claim. A 2024 paper, a high-resolution search for CCC signatures, reports additional problems. The authors find that unusually bright or dark pixels in the CMB maps, spots, can generate spurious regions with many low-variance circles under the criteria used in earlier CCC work. After removing these spot contaminants, they report no statistically significant evidence for either low-variance circles or Hawking points. The paper is careful to note that non-detection does not logically disprove conformal cyclic cosmology. The theory could still be true while producing signatures too weak to detect with current instruments. It indicates that the claimed strong observational evidence does not survive more conservative statistical treatment. This is the current state of the observational dispute. The 2018 paper claims detection at 99.98% confidence. The 2020 reanalysis argues significance drops to approximately 87%, 1 sigma, after accounting for the look elsewhere effect. The 2024 high-resolution search reports no statistically significant evidence after cleaning spot artifacts. Conformal Cyclic Cosmology remains a theoretical framework under active development. A 2025 paper by Meissner and Penrose reframes the crossover physics, embedding Hawking points as discrete features in the conformal geometry and proposing a mass-energy conservation law across the crossover. The paper also acknowledges a tension. The observed angular diameter of Hawking point candidates is about twice what earlier framing predicted. This is a theory development step, not a resolution. I want to dwell on the forensic dispute for a moment, because it illustrates something important about how science works and how extraordinary claims require extraordinary evidence. The 2018 Hawking points paper uses a specific methodology. The authors identify circular regions in the CMB temperature maps, compute the temperature variance within those circles, and look for regions with anomalously low or high variance. They scan over circle radii from 0.03 to 0.04 radians and select the most significant results. They then check whether the same sky locations show anomalies in both WMAP and Planck data. This is a reasonable approach. It has a statistical vulnerability, the look elsewhere effect. Imagine you are searching for a rare signal. You do not know exactly what size it will be, so you search over a range of sizes. You do not know exactly where it will be, so you search over the whole sky. At each size and each location, you compute a statistical test. Some results will look significant just by chance, random fluctuations that happen to align with your search criteria. If you then report only the most significant result across all the sizes and locations you searched, you have effectively performed many statistical tests and cherry-picked the best one. The apparent significance is inflated. A result that looks like 99.98% confidence when considered in isolation might be much less significant when you account for all the places you looked. This is the look elsewhere effect. It is a well-known issue in particle physics, astronomy, and any field where you search for signals without knowing exactly where they will appear. The proper treatment is to marginalize over the search parameters to account for the fact that you scanned over ring sizes, sky locations, and other variables. The Zhao and Scott reanalysis does exactly this. When they marginalize over the range of ring sizes that the 2018 paper scanned, the significance drops from 99.98% to about 87%. This is the difference between a potentially important detection and a statistical fluctuation. The 2024 high-resolution search adds another layer. The authors find that bright or dark pixels in the CMB maps, spots caused by point sources, instrument artifacts, or residual foreground contamination can generate spurious regions that look like anomalous circles under the 2018 criteria. When they identify and remove these spot contaminants, the claimed signals disappear. This is how forensic science works. You start with a claim. You test the claim against alternative explanations. If the claim survives, if there is no plausible alternative, the claim is strengthened. If the claim does not survive, if the alternative explanations account for the data, the claim is weakened. The Hawking point claim does not survive conservative statistical treatment. This does not mean conformal cyclic cosmology is wrong. It means the observational evidence claimed to support CCC is not robust. The theory remains possible. The detection is not established. And conformal cyclic cosmology has faced observational challenges before. In 2010, Roger Penrose and astrophysicist Vahe Ghazadian published a paper claiming to find concentric low-variance circles in the CMB, an earlier proposed signature of CCC. Multiple independent reanalyses followed, criticizing the statistical methods and arguing that the claimed anomalies were consistent with noise. The low-variance circle claim is now generally regarded as not established. The pattern is consistent. Conformal cyclic cosmology generates specific observational predictions. Those predictions are tested. The tests reveal statistical issues. The claimed detections do not survive conservative treatment. This is not a failure of conformal cyclic cosmology specifically. It is the normal process of science. Bold theories make predictions. Predictions are tested. Sometimes the predictions are confirmed. Sometimes they are not. What matters is that the process continues, that claims are tested rather than accepted on authority. The conformal factor problem also deserves mention. For CCC to work, the conformal factor, omega, the function that rescales the metric, must be chosen in a specific way at the crossover. A paper by physicists Oliver Markwell and Chris Stevens emphasizes that choosing this conformal factor uniquely is a major open hurdle. They compare proposed prescriptions and rule out certain choices. The freedom in choosing omega means that conformal cyclic cosmology does not yet have a unique, well-defined crossover prescription. This is a theoretical incompleteness separate from the observational issues. Mathematical physicist Paul Todd has contributed to clarifying what conformal matching can and cannot mean in the CCC context. The matching requires that certain quantities, the conformal structure, certain tensor fields, be smooth across the crossover. Whether physical quantities like energy and information are preserved, transformed, or lost is model-dependent and not fully settled. These are active research questions. Conformal cyclic cosmology is a living framework under development by Roger Penrose and collaborators. The 2025 paper by Meissner and Penrose is the latest iteration, refining the crossover description and attempting to address earlier tensions. The framework has not yet produced a confirmed observational signature. The hunt continues. What would you conclude from this evidence? This is the part that stays with me. Not the theoretical possibility of cosmic cycles, that is a legitimate area of research. The gap between what is claimed and what is established. The 2018 paper uses language like apparent evidence and strong observational evidence. The subsequent reanalyses find that this evidence is not robust under conservative statistical treatment. Yet the claim, Hawking points detected, previous aeon observed, circulates as if it were settled. It is not settled, it is contested, and the contest is ongoing. Let me now return to the broader question of cyclic cosmologies and the thermodynamic obstacles they face. Even setting aside CCC's specific observational claims, cyclic cosmologies face a general challenge: entropy. And entropy is not a minor technical detail. It is arguably the deepest constraint on any theory of cosmic cycles. The second law of thermodynamics states that entropy in a closed system does not decrease. Entropy is a measure of disorder, of the number of ways a system can be arranged while still looking the same macroscopically. High entropy means many possible arrangements. Low entropy means few. And physical systems tend to move from low entropy states to high entropy states, not because they are pushed in that direction, but because high entropy states are overwhelmingly more numerous. The early universe had low entropy, extraordinarily low. The CMB is uniform to 1 part in 100,000. If you shuffle the matter in the early universe while keeping the temperature the same, there are very few arrangements consistent with that uniformity. This is a low entropy state. Today, entropy is higher. Stars have formed and are radiating away energy. Black holes exist, and black holes have enormous entropy. The Bekenstein-Hawking formula gives entropy proportional to horizon area, and a single stellar mass black hole has more entropy than all the ordinary matter in the observable universe at the time of the CMB. In the far future, entropy will be higher still. Stars will burn out, stellar remnants will cool, black holes will grow, merge, and eventually evaporate. The universe will approach thermal equilibrium, maximum entropy for the available energy and volume. Now consider a cyclic cosmology. If the universe cycles, if there is a big crunch followed by a new big bang, or a conformal matching between aeons, or a bounce mediated by some exotic physics, then what happens to entropy at the transition? If entropy carries over from one cycle to the next, it must increase with each cycle. The second law demands it. Increasing entropy from cycle to cycle means that early cycles had lower entropy than later cycles. This creates a puzzle. Why would the first cycle have such low entropy? Where did the low entropy initial condition come from? If entropy is somehow reset at the transition, reduced rather than carried over, then the second law is violated locally. This is not impossible in principle. The second law is statistical, not absolute, but it requires an explanation. What mechanism decreases entropy at the transition? How does it work? Is it consistent with known physics? A 2024 paper by physicist Petar Pavlovich analyzes how cyclicity and entropy growth interact. The paper emphasizes that models in which the scale factor is strictly periodic, where the universe expands and contracts in repeating identical cycles, generically face an entropy density divergence problem. Entropy density grows without bound from cycle to cycle. Eventually, the cycles become incompatible with the conditions required for structures like stars, planets, and observers. The mathematics is direct. If each cycle produces entropy delta S, and if the volume of the universe returns to the same value at the start of each cycle, then the entropy density increases by delta S over V each cycle. After n cycles, entropy density has increased by n times delta S over V. As n goes to infinity, entropy density diverges. The system eventually reaches a state where no more structure formation is possible, heat death within each cycle. Pavlovich then examines escape hatches, non-periodic Hubble parameter. If the rate of expansion varies from cycle to cycle in specific ways, entropy might be distributed differently. Nearly empty phases. If each cycle includes a phase where the universe is nearly empty of matter and radiation, entropy can be diluted or partitioned into gravitational degrees of freedom that do not affect ordinary matter. Expanding scale factor between cycles. If each cycle is larger than the previous, if the universe grows overall even as it oscillates, entropy density can remain bounded because the volume grows faster than entropy. These escape hatches are logically possible. They are not obviously realized in nature. They require specific assumptions about the dynamics at the bounce or transition, and they do not automatically produce the low entropy initial conditions needed for structure formation in each cycle. Conformal cyclic cosmology has its own approach to the entropy problem. Roger Penrose argues that black holes represent enormous gravitational entropy, and that when black holes evaporate, this entropy is released back into radiation. By the time all black holes have evaporated, the universe consists only of radiation, and radiation, Roger Penrose argues, has low gravitational entropy because gravity has not clumped it into structures. The conformal matching then identifies this late-time radiation-dominated state with a new Big Bang. The new aeon starts with radiation, which will later clump under gravity into stars and galaxies and black holes, increasing gravitational entropy again. Each aeon starts fresh in some sense, even though the conformal matching connects them. Whether this actually solves the entropy problem is debated. The gravitational entropy of black holes is enormous. That is not disputed. Whether the entropy goes away when black holes evaporate, or whether it is carried by the Hawking radiation in a form that still contributes to the entropy budget, is a subtle question tied to the black hole information paradox. The black hole information paradox is one of the deepest open questions in theoretical physics. When a black hole evaporates, is the information about what fell in preserved in the Hawking radiation, or is it lost? If information is preserved, if the process is unitary, as quantum mechanics seems to require, then the entropy of the Hawking radiation must somehow encode the information. If information is lost, quantum mechanics is violated in gravitational contexts. Conformal cyclic cosmology sometimes seems to assume that information is effectively lost in black hole evaporation, that the Hawking radiation is truly thermal and carries no memory of what formed the black hole. This would make the entropy disappear along with the black hole. Most modern approaches to quantum gravity, including string theory and the ADS/CFT correspondence, suggest information is preserved. The debate is not settled. This is another conditional in the chain. CCC's entropy solution depends on assumptions about black hole evaporation that are not universally accepted. A 2016 paper by physicist Ferreira studies thermodynamics of non-singular bouncing universes within general relativity and argues that such models can violate the generalized second law away from the bounce under the assumptions used there. This is a hard constraint paper, one that identifies specific tensions between bounce cosmology and thermodynamics. Cyclic and bounce models must address these tensions, not ignore them. The ekpyrotic and cyclic family of models, reviewed by theoretical cosmologist Jean-Luc Lehners, represents a major non-CCC approach to cyclicity. These models typically involve a phase of ultra-slow contraction that smooths and flattens the universe, followed by a bounce, potentially repeating. They aim to reproduce the observed large-scale homogeneity and near-scale invariant density perturbations without invoking cosmic inflation. They face technical challenges, generating scale-invariant perturbations without instabilities, managing entropy across cycles, matching the detailed constraints from CMB observations. Let me describe the ekpyrotic scenario in more detail because it represents a genuinely different approach to the cyclicity question. The name ekpyrotic comes from the ancient Greek philosophy of periodic conflagration, the idea that the universe is periodically destroyed by fire and reborn. In modern physics, the ekpyrotic scenario was developed in the early 2000s, building on ideas from string theory and brain cosmology. The basic picture is this. Our universe is a three-dimensional brain, a membrane-like object embedded in a higher dimensional space. A second brain exists parallel to ours, separated by a gap in the extra dimension. Occasionally, the brains collide. The collision releases enormous energy, heating our brain and triggering what we experience as the Big Bang. Before the collision, the brains are nearly flat and nearly parallel, smoothed out by their dynamics in the higher dimensional space. This is how the scenario generates the uniformity we observe. Not through inflationary expansion, but through a phase of contraction in the extra dimension that flattens the brains. The key prediction is the spectrum of density perturbations. Cosmic inflation predicts nearly scale-invariant perturbations, the same amplitude at all length scales up to small corrections. The ekpyrotic scenario also predicts nearly scale-invariant perturbations, but generated by a different mechanism, the contraction phase rather than the expansion phase. Distinguishing between the two requires precise measurements of the perturbation spectrum and, ideally, of gravitational waves from the early universe. The challenge is that generating exactly the right perturbation spectrum in ekpyrotic models is technically difficult. Early versions had problems with instabilities or with producing tilts in the spectrum that did not match observations. Subsequent work by Lehnes and collaborators has refined the models addressing some of these issues. No ekpyrotic model has achieved the level of data-fitting success that inflationary lambda-CDM has. Cyclicity in the ekpyrotic framework comes from the idea that the brain collision repeats. After each collision, the brains separate, move apart, turn around, and collide again. Each collision is a new Big Bang. Each separation is a new cycle. The entropy problem is addressed in ekpyrotic cyclicity by proposing that entropy is diluted during the expansion phase and reset at the collision. The details are model-dependent and not fully worked out. This is an active research area, not a finished theory. Alternatively, loop quantum cosmology, LQC, applies loop quantization techniques to homogeneous cosmologies and often yields effective dynamics in which the Big Bang singularity is replaced by a quantum bounce at Planckian densities. LQC is frequently discussed as a candidate mechanism for a big bounce, but observationally distinguishing LQC bounce signatures from inflationary or other early universe scenarios remains difficult. The key insight of loop quantum gravity, the parent theory from which LQC is derived, is that space itself is quantized. At the Planck scale, space is not continuous but discrete, consisting of finite quanta of area and volume. This discreteness becomes relevant when curvature approaches Planck scale values, precisely the situation at the Big Bang singularity. In classical general relativity, the Big Bang is a singularity, a point of infinite density, infinite temperature, infinite curvature. The equations break down. Physics cannot describe what happens at or before the singularity. In loop quantum cosmology, the singularity is avoided. As the universe contracts and approaches Planck scale density, quantum gravitational effects become important. The effective repulsion from quantum geometry prevents the density from diverging. Instead of a singularity, there is a bounce, a minimum size and maximum density, after which the universe begins expanding again. This is a tantalizing result. It suggests that the Big Bang was not the beginning of everything, but a transition from a prior contracting phase. The prior phase could itself have been preceded by another bounce, and so on, potentially eternally. The predictions of LQC for observable quantities, the spectrum of CMB fluctuations, the amplitude of gravitational waves, the presence of anomalies in the primordial perturbations, are subtle and model-dependent. Different implementations of LQC give different predictions. Distinguishing these predictions from the predictions of standard cosmic inflation requires precision that current observations are only beginning to approach. The thermodynamic issues also apply to LQC bounces. If the universe bounces rather than beginning at a singularity, what happens to entropy? Does entropy accumulate across bounces? Is there an entropy reset mechanism? These questions are active research topics in loop quantum cosmology. A 2024 preprint proposes a cyclic bouncing universe construction using instant folded strings within string theory, claiming the bounce can be described with theoretical control. This is an example of string-motivated cyclic work that tries to provide a specific bounce mediator rather than just a phenomenological scale factor prescription. The authors claim that the IFS mechanism allows for a precise description of the bounce, unlike purely effective theory approaches that treat the bounce as a black box. The pattern across all these approaches is consistent. Cyclic cosmology is an active research area with multiple theoretical frameworks under development. None has achieved the status of established science. None has produced definitive observational signatures that distinguish it from the standard inflationary lambda-CDM model. The theoretical work is ongoing. The observational tests are challenging. The entropy constraints are serious but not insurmountable with the right assumptions. And what is the standard model? The operational default framework used to fit CMB observations is spatially flat 6-parameter lambda-CDM with adiabatic initial conditions, typically paired with an early cosmic inflation phase in the broader narrative. The Planck satellite's final cosmological parameter paper, the 2018 legacy release, reports internal consistency of lambda-CDM across temperature, polarization, and lensing datasets. It quotes precise parameter constraints. Age of the universe: 13.797 plus or minus 0.023 billion years. Hubble constant, 67.4 plus or minus 0.5 kilometers per second per megaparsec. CMB monopole temperature, 2.7255 Kelvin, about negative 454.76 degrees Fahrenheit, or 270.42 degrees Celsius below zero. Recombination redshift, the moment when the CMB was released, approximately 1090. These are the baseline numbers. They anchor the thermal history of the universe. They are used in essentially all early universe alternatives, including Conformal Cyclic Cosmology, as reference points. Conformal Cyclic Cosmology does not challenge these numbers. CCC challenges the interpretation of what came before the epoch described by these numbers. CCC is compatible with conventional lambda-CDM history. After very early times, after about 10 to the negative 35 seconds, while adding proposed inputs from a previous aeon. The 2018 Hawking Points paper explicitly states that CCC is not in any major way in conflict with lambda-CDM after that epoch. This is an important point. Conformal cyclic cosmology is not a rejection of mainstream cosmology. It is an extension of it, a proposal for what happened before cosmic inflation, for what set the initial conditions, for why the early universe had such low gravitational entropy. The low entropy of the early universe is one of Roger Penrose's primary motivations for conformal cyclic cosmology. The Big Bang was extraordinarily uniform. The CMB is isotropic to 1 part in 100,000 after removing the dipole contribution from our motion through space. This uniformity corresponds to very low gravitational entropy. If gravity had been important in the early universe, if structures like black holes had existed, the entropy would have been vastly higher. Roger Penrose argues that this low entropy initial condition is a puzzle requiring explanation. Cosmic inflation, he claims, does not solve the puzzle because time-symmetric dynamics cannot generically generate a low entropy boundary. Something special must have happened at or before the Big Bang to select such an improbable state. Think about that for a moment. The entropy of the early universe was extraordinarily low, not because entropy is always low, but because the initial state was special, selected. Among all the possible initial conditions the universe could have had, the actual initial condition was one in an astronomically small fraction, the tiny minority of states that would lead to a universe like ours. Why? The standard inflationary model does not answer this question. Cosmic inflation explains how a small, smooth patch of space could expand into the large, smooth universe we observe. It does not explain why that small, smooth patch existed in the first place. It pushes the question back, but does not eliminate it. Conformal cyclic cosmology offers a different answer. The low entropy Big Bang is connected to the high entropy end of a previous aeon through conformal matching. The remote future, after black holes have evaporated, consists only of radiation. Radiation, Roger Penrose argues, represents low gravitational entropy because gravity has not clumped it. The conformal matching identifies this state with a new Big Bang which inherits the low gravitational entropy. Whether this actually explains the low entropy or merely relocates the problem is debated. If the previous aeon also began with low entropy, where did that come from? Conformal cyclic cosmology proposes an infinite sequence of aeons with no first aeon. The low entropy of each Big Bang is inherited from the high to low entropy transformation at the end of the previous aeon, all the way back without beginning. Some find this satisfying, others find it unsatisfying, an infinite regress rather than an explanation. The question of why there is something rather than nothing, why the initial conditions were special, remains at the edge of what physics can address. Science can describe what happens and how it happens. It can measure entropy bounds, it can prove recurrence theorems, it can fit cosmological parameters to unprecedented precision. The question of why anything exists at all, why there is a universe that can be described, why laws that can be measured, why initial conditions that can be puzzled over, that question does not have a scientific answer. It sits at the boundary where physics ends and something else begins. Philosophy, perhaps, or simply mystery, acknowledged but not dissolved. Some questions may simply be beyond what science alone can address. This is not a failure of science. It is a recognition of scope. Science is the method for understanding the physical world through observation, experiment, and mathematical description. It has been extraordinarily successful. There are questions that are not empirical, questions that cannot be answered by observation, because they are about why observation is possible at all, why there is anything to observe. The recurrence argument touches this boundary. It extrapolates from finite entropy to finite states to eventual return. The extrapolation is valid under its assumptions. The question of whether the assumptions hold, whether time is truly infinite, whether the dynamics permit recurrence, whether identity persists across repetition, these are questions that may never have definitive answers. And the claim, "you have lived this exact life trillions of times before," remains conditional. True if the premises are true. Unknown if the premises are unknown. And at least one premise, the metaphysics of identity, may not have a fact of the matter to be discovered. Let me now turn to the concrete data that underlies all these discussions, the cosmic microwave background itself. The CMB is the thermal relic radiation from the early universe, light released about 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and the plasma to become transparent. It has been traveling through space ever since, stretched by cosmic expansion from visible light to microwave wavelengths. The relationship between temperature and redshift is direct. T of z equals T0 times 1 plus z. At recombination, Z was about 1090. The temperature then was about 3000 Kelvin. Today, T0 is 2.72548 Kelvin, about negative 270 degrees Celsius, or negative 454 degrees Fahrenheit, just 2.7 degrees above absolute zero. The first precision measurement of the CMB spectrum came from the COBE satellite's FIRUS instrument, launched by NASA in 1989. FIRUS confirmed that the CMB is an extremely good blackbody, thermal radiation following the Planck distribution with essentially no deviations at the sensitivity level of the instrument. The deviations are constrained to less than about 1 part in 10,000 of the peak brightness. This is one of the most perfect blackbody spectra ever measured in nature. It confirms that the early universe was in thermal equilibrium, that the photons and matter were strongly coupled, exchanging energy freely before the plasma became transparent. WMAP, the Wilkinson Microwave Anisotropy Probe, was launched by NASA in June 2001 and provided full-sky CMB temperature and polarization maps at higher resolution than COBE. WMAP operated for 9 years, producing multiple data releases that progressively refined the cosmological parameter measurements. WMAP data is explicitly used in the Hawking Points papers as an independent check. If the same anomalous spots appear in both WMAP and Planck maps, the argument goes they are less likely to be instrument noise. WMAP's resolution was about 0.2 degrees, roughly the diameter of the Moon. This was sufficient to map the acoustic peaks in the CMB power spectrum, which encode information about the universe's composition and geometry. It was not sufficient to detect small-scale features like potential Hawking points, which have diameters of 3 to 4 degrees. For Hawking point searches, what matters is temperature precision at a given location, not angular resolution per se. Planck, launched by the European Space Agency in May 2009, provides the highest resolution multi-frequency CMB observations to date. Planck observed at 9 frequency bands from 30 to 857 GHz, allowing detailed separation of the CMB from foreground contamination. Synchrotron radiation from our galaxy, thermal dust emission, free radiation, and extragalactic sources. The component-separated maps, including the widely used SMICA map, have an effective resolution of about 5 arc minutes, roughly 100 times finer than WMAP's. Planck's final cosmological parameter release, the 2018 legacy paper, reports the numbers that anchor modern cosmology. Age of the universe, 13.797, plus or minus 0.023 billion years. That uncertainty, 23 million years, is less than 1% of Earth's age, less than 1% of the time since the dinosaurs went extinct. We know the age of the universe to extraordinary precision. Hubble constant, 67.4 plus or minus 0.5 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light-years, galaxies are receding at an additional 67.4 kilometers per second due to cosmic expansion. The corresponding Hubble time, 1 over h0, is about 14.5 billion years. The corresponding Hubble length, c over h0, is about 14.4 billion light-years, or about 4.4 gigaparsecs. Matter density, about 31.5% of the critical density, with ordinary baryonic matter contributing about 5% and dark matter about 26.5%. Dark energy density, about 68.5% of the critical density, the dominant component driving accelerated expansion. Curvature, consistent with zero, a spatially flat universe. These numbers are not guesses, they are fits to data, specifically to the pattern of temperature fluctuations in the CMB, which encodes information about the universe's composition and dynamics at the time of recombination. The fit is excellent. The lambda-CDM model with these parameters reproduces the observed CMB power spectrum across a wide range of angular scales. Fitting the data is not the same as explaining the data. The lambda-CDM model tells us what the universe is made of: dark matter, dark energy, ordinary matter, radiation. It doesn't tell us what dark matter is, what dark energy is, why the cosmological constant has the value it does, or why the initial conditions were what they were. These are open questions. Conformal cyclic cosmology does not challenge the lambda-CDM fit. CCC challenges the interpretation of what came before the epoch described by these numbers. Let me now trace the historical timeline of ideas that led us here, because the question of cosmic recurrence did not begin with Roger Penrose. It is older than modern cosmology itself. In 1890, mathematician Henri Poincaré proved what is now called the Poincaré recurrence theorem. Working in the context of classical mechanics, the physics of Newton, Lagrange, and Hamilton, Henri Poincaré showed that for a system with a bounded phase space evolving under measure-preserving dynamics, almost every initial state will eventually return arbitrarily close to itself. The theorem was abstract, mathematical. Its implications were vast. In a finite, closed system, the future eventually resembles the past. States recur. This was a mathematical result, not a physical claim about the universe. Henri Poincaré was studying the three-body problem, the motion of three gravitating objects, and encountered the theorem as a consequence of the mathematical structure of Hamiltonian mechanics. The theorem raised questions. If the universe is a closed system, does recurrence apply to it? In 1957, physicists Bocchieri and Loinger extended Poincaré's result to quantum mechanics. They proved that for a closed quantum system with a discrete energy spectrum, the quantum state returns arbitrarily close to its initial state after sufficiently long time. This is the Quantum Recurrence Theorem, the mathematical backbone of the configurations must repeat premise. The proof is rigorous. The conditions are specified. Under those conditions, recurrence is guaranteed. In 1977, Gary Gibbons and Stephen Hawking published their foundational paper on the thermodynamics of cosmological horizons. They showed that de Sitter space, a universe with a positive cosmological constant, has a temperature and an entropy just as black holes do. The temperature is proportional to the Hubble parameter. The entropy is proportional to the horizon area. This paper connected cosmology to thermodynamics in a way that had not been done before. It implied that the far future of an accelerating universe has finite entropy and potentially finite information. In 1981, Jacob Bekenstein published his Universal Entropy Bound, the relationship between energy, size, and maximum entropy that bears his name. This bound became the conceptual foundation for arguments about finite information in physical systems. If entropy is bounded, states are bounded. If states are bounded and time is infinite, recurrence follows. In 1999, Raphael Bousso proposed the covariant entropy bound, a refinement of Bekenstein's ideas designed to work in dynamical spacetimes and gravitating systems. The covariant bound uses light sheets rather than spatial volumes, making it applicable to cosmology. This became the more rigorous foundation for entropy arguments in expanding universes. In 2002, Lisa Dyson, Matthew Kleben, and Leonard Susskind published their analysis of recurrence in de Sitter space. They connected the finite entropy of the cosmological horizon to recurrence times, noted the Boltzmann brain problem, and framed these as paradoxes requiring resolution. Their paper brought recurrence arguments into mainstream cosmological discussion. In 2006, Roger Penrose publicly outlined Conformal Cyclic Cosmology, proposing that the remote future of one aeon could be conformally matched to the Big Bang of the next. This was a specific mechanism for cosmic cyclicity, grounded in the mathematics of conformal geometry. In 2010, Roger Penrose and Vahe Gurzadian published claims of concentric low-variance circles in the CMB as potential CCC signatures. Multiple reanalyses followed, criticizing the statistical methods. The low variance circle claim is now generally regarded as not established. In 2018, the Hawking Points paper claimed detection of circular hotspots in the CMB at 99.98% confidence, fossil signatures of prior aeon black holes. This was the strongest observational claim for conformal cyclic cosmology to date. In 2020, Dylan Zhao and Douglas Scott published their reanalysis, showing that the claimed significance drops to approximately 1 sigma after accounting for the look elsewhere effect. The detection claim was called into question. In 2024, a high-resolution CCC signature search found that spot contamination could explain the claimed anomalies. After cleaning, no statistically significant evidence remained. In 2025, Christoph Meissner and Roger Penrose published a refined CCC formulation acknowledging angular size tensions while continuing theory development. This is the timeline, from Henri Poincaré's abstract theorem in 1890 to the ongoing CCC dispute in 2025. Over a century of ideas about recurrence, entropy, and the far future of the universe. The mathematics has been refined, the physics has been extended, the observational tests have been attempted. The question remains open. Conformal cyclic cosmology proposes an explanation for the initial conditions, why the early universe was so uniform, why gravitational entropy was so low. Whether that explanation is correct is the question under investigation. Ground-based observatories, including ACT, the Atacama Cosmology Telescope, and SPT, the South Pole Telescope, provide even higher resolution over smaller sky areas. ACT's data release 6 reports arc-minute resolution CMB maps across 3 frequency bands with wide sky coverage. SPT-3G is designed for arc-minute scale mapping at 95, 150, and 220 GHz. These instruments are relevant because CCC signature searches repeatedly encounter resolution and systematics limitations. Higher resolution could sharpen or refute specific predictions if the predictions are made precise enough. Lightbird, a planned Japanese space mission, is aimed at very sensitive large-scale CMB polarization, especially B modes that could signal primordial gravitational waves from cosmic inflation. Lightbird's expected launch is in Japanese fiscal year 2032, though schedule uncertainty remains. This matters because CCC type claims that invoke subtle, low-amplitude signatures increasingly require next-generation data quality and systematics control. If Hawking points are real but weak, future missions might detect them with higher confidence. If Hawking points are statistical artifacts, future missions will not find them. The CMB is one statistical realization of a random field. We have one sky. We cannot observe the CMB from another location in the universe. This single sky limitation makes anomaly hunting structurally vulnerable to a posteriori pattern selection. If you search for enough patterns, you will find some that look unusual by chance. The look elsewhere effect applies. This limitation is fundamental, not technical. It cannot be overcome by better instruments. We have one CMB. That CMB is a single draw from a probability distribution. Features that look unusual might be rare fluctuations in that single draw, or they might be genuine signals. Distinguishing the two requires careful statistical treatment and honest acknowledgement that some questions cannot be answered with a single sample. The speed of light imposes another limitation. We can only observe our past light cone, the region of space-time from which light has had time to reach us since the Big Bang. Beyond the cosmological horizon, events are causally disconnected from us. We cannot know what is happening there. We cannot verify whether recurrence occurs there. The observable universe is a subset of whatever exists. CCC's claimed signals are unusual in this context. If Hawking points are fossil signatures of prior aeon black holes, they are information that survived the conformal crossover, information from before the Big Bang of our aeon. This is not ordinary causal propagation. The prior aeon is not in our past light cone in any standard sense. The conformal matching is a mathematical identification, not a causal connection. This makes CCC's predictions both interesting and difficult to test. If the crossover erases most information, but preserves specific signatures, detecting those signatures would be extraordinary evidence. It also means the prior aeon is fundamentally inaccessible. We cannot observe it directly, only through whatever fossils survive the matching. CMB maps are also not raw data. They are reconstructed after foreground subtraction and component separation, removing contamination from our galaxy, from extragalactic sources, from instrument noise. Bright or dark pixel artifacts from imperfect cleaning can mimic special features. This is why the 2024 high-resolution CCC search emphasizes spot contamination as a source of spurious low-variance circles. The process of component separation is sophisticated. Planck observed at 9 frequency bands precisely so that foreground contributions, which have different spectral signatures than the CMB, could be modeled and subtracted. No model is perfect. Residual contamination remains, and the residuals can correlate with search criteria in ways that inflate apparent significance. These are limitations, not dismissals. The CMB remains our best window into the early universe. Interpreting features in the CMB requires careful statistical treatment, and claims of detections must survive that treatment. The thermodynamic limitation is also fundamental. Any cyclic or bounce model must reconcile cycles with entropy growth, or explain the mechanism by which entropy is managed across transitions. This is not an aesthetic preference. It is a constraint from the deepest laws of physics we know. The second law of thermodynamics is not negotiable. Models that violate it, or that hand-wave about entropy without providing a mechanism, are incomplete. Let me now return to the theoretical chain connecting entropy bounds to recurrence. I have discussed the Bekenstein bound and the covariant entropy bound as foundations for the finite information premise. I have discussed the Quantum Recurrence Theorem as the mathematical backbone for the configurations must repeat premise. I have noted that the recurrence timescale is e to the s, incomprehensibly long but finite. There is another piece of the puzzle: de Sitter thermodynamics. If the universe has a positive cosmological constant, and observations strongly suggest it does, then in the far future, the universe will approach a de Sitter state. A de Sitter universe has a cosmological horizon, a surface beyond which events can never affect us because the space between us is expanding too fast for even light to cross. This is not a property of distant objects moving faster than light through space. The objects are not moving at all in their local reference frames. Rather, the space between us and them is expanding. At a certain distance, the Hubble radius, the rate of expansion times the distance, equals the speed of light. Beyond that distance, Recession due to expansion exceeds what light can overcome. Events there are causally disconnected from us. They are beyond our horizon. In 1977, physicists Gary Gibbons and Stephen Hawking derived the temperature and entropy of this cosmological horizon. The derivation used techniques from quantum field theory in curved spacetime, the same techniques Stephen Hawking had used in 1974 to derive black hole radiation. The result is that the cosmological horizon, like a black hole horizon, has thermodynamic properties. The de Sitter temperature is T equals h bar h over 2 pi k. H is the Hubble parameter, the rate of expansion, currently about 67.4 kilometers per second per megaparsec, or about 2.2 times 10 to the negative 18 per second. H bar is the reduced Planck constant. K is the Boltzmann constant. Plugging in the numbers, the de Sitter temperature is approximately 2.4 times 10 to the negative 30 Kelvin. This is unfathomably cold. The cosmic microwave background at 2.7 Kelvin is 10 billion trillion times hotter than the de Sitter temperature. The de Sitter state is asymptotic, approached after all other sources of energy have dissipated, and extremely dilute. It has a temperature. It has thermal fluctuations. The de Sitter entropy is S equals Ka over 4 Lp squared. A is the horizon area. Lp is the Planck length, approximately 1.6 times 10 to the negative 35 meters. For the current cosmological horizon, with a radius of about 1.4 times 10 to the 26 meters, the area is about 2.5 times 10 to the 53 square meters. Divided by 4 times the Planck area, the entropy is about 10 to the 122 in natural units, where K equals 1. This is an enormous number. It is finite, and this finite entropy implies a finite number of accessible states for an observer inside the horizon. If the universe persists as a de Sitter space for infinite time, and if the dynamics are such that the Quantum Recurrence Theorem applies, then recurrence should eventually occur. This is where the recurrence paradox papers come in. Lisa Dyson, Matthew Kleben, and Leonard Susskind, writing in 2002, explored the consequences of a universe with a positive cosmological constant and finite horizon entropy. They noted that if recurrence occurs, it leads to strange conclusions. One is the Boltzmann brain problem. If the universe persists for timescales comparable to the recurrence time, random thermal fluctuations in the de Sitter vacuum should occasionally produce any structure, including conscious observers. A fluctuation that produces a minimal observer, a Boltzmann brain floating in empty space with just enough structure to have a brief conscious experience, is far more probable than a fluctuation that produces an entire universe with galaxies and planets and biospheres and billions of years of history. If recurrence and thermal fluctuations dominate the far future, then typical observers should be Boltzmann brains, not organisms that developed over billions of years. We do not appear to be Boltzmann brains. Our memories are consistent with a long history. The universe around us is consistent with 13.8 billion years of cosmological development. If we take this apparent history at face value, we are not typical fluctuation observers. We are products of structure formation in a low entropy universe. This creates a tension. If the future is dominated by recurrence and fluctuations, and if observers are selected from this future ensemble, then we should be fluctuation observers. We do not appear to be. Either our apparent history is an illusion, we are Boltzmann brains with false memories, or something prevents the recurrence regime from dominating the observer population. Dyson, Kleban, and Susskind treat this as a paradox to be resolved, not a prediction to be accepted. Possible resolutions include vacuum decay. The de Sitter vacuum might be metastable. A transition to a lower energy state could occur, ending the de Sitter phase before recurrence timescales are reached. Horizon complementarity. Different observers might have access to different portions of space-time, and the global space-time, including recurrence, might not be the right object to consider for observer statistics. Measure problems. How you count observers in an infinite or eternally fluctuating space-time is subtle. Different counting procedures give different answers about what is typical. None of these resolutions is universally accepted. The Boltzmann brain problem is an active area of research in cosmology and philosophy of physics. It illustrates that naive extrapolations from recurrence theorems can lead to conclusions that seem absurd, and absurd conclusions motivate revisiting the assumptions. This connects to the broader question of eternal inflation and the multiverse. In eternal inflation models, inflation continues indefinitely in some regions of spacetime, producing an infinite number of pocket universes like ours. Each pocket universe has its own history, its own physical constants, its own outcomes. The ensemble of all pocket universes is vast, potentially infinite. If the multiverse is infinite and eternal, then every possible configuration that can occur will occur, not just once, but infinitely many times. This includes not only copies of you, but copies of you making different choices, experiencing different outcomes, living in universes with different laws of physics. The question of what is typical becomes even more complex in an infinite multiverse. Whether eternal inflation actually occurs depends on the details of inflationary physics and the landscape of possible vacuum states. Current observations are consistent with a phase of early inflation in our observable universe, but they do not directly constrain whether inflation continues elsewhere. The multiverse remains a theoretical possibility, not an established fact. Let me now bring the investigation to a synthesis. The claim, "You have lived this exact life trillions of times before," rests on a chain of conditional premises. Premise 1. Finite information in the causal patch. Status, supported by entropy bounds, Bekenstein, covariant, but the precise value depends on the horizon structure and the definition of entropy in quantum gravity. Premise 2. Finite information implies finite states. Status, supported by statistical mechanics, with the number of states scaling exponentially with entropy. Premise 3. Finite states plus infinite time implies recurrence. Status, supported by the Quantum Recurrence Theorem, under assumptions about the system's dynamics that cosmology does not settle. Premise 4. Time is infinite. Status, not proven. Depends on the absence of vacuum decay, phase transitions, or other future cutoffs. Premise 5. Recurrence includes your specific configuration. Status requires ergodicity or equivalent assumptions, plus a definition of what counts as you. Each premise has support. Each premise has conditions. The chain is valid, but conditional. The observational evidence that would strengthen the case, Conformal Cyclic Cosmology's claimed Hawking points, is contested. The 2018 claim of 99.98% confidence detection drops to approximately 1 sigma after accounting for the look elsewhere effect. Independent reanalyses find no statistically significant evidence for Hawking points or low variance circles after cleaning spot contamination. Conformal cyclic cosmology remains a theoretical framework under active development. It is not established, it is not refuted, it is contested. The thermodynamic obstacles to cyclic cosmologies, entropy growth across cycles, remain active research topics. Escape hatches exist but require specific assumptions. The standard lambda-CDM cosmological model fits the data. It gives us precise numbers: the age of the universe, the Hubble constant, the matter and energy densities, the geometry of space. It does not explain the low entropy initial conditions. It does not tell us what dark matter is, what dark energy is, why the cosmological constant has its observed value. These are open questions. We can describe what the universe is like. We can calculate its parameters to extraordinary precision. We can derive recurrence theorems that apply under specified conditions. We can compute entropy bounds that constrain information content. The question of why these particular conditions obtained, why there is something rather than nothing, why these laws and not others, why an initial state of such extraordinarily low entropy sits beyond the reach of telescopes and equations. Science maps the boundary of this question. Science does not cross it. Some questions may simply be beyond what science alone can address. I began this investigation with a claim: you have lived this exact life trillions of times before. I have traced the chain of premises. I have presented the evidence for each. I have presented the challenges. I have been precise about what is established and what is conditional. The cosmic microwave background preserves the light from 380,000 years after the Big Bang. The Planck satellite has mapped it at 5 arc-minute resolution, determining cosmological parameters to percent-level precision. The Bekenstein Bound constrains entropy to finite values. The Quantum Recurrence Theorem guarantees return under suitable conditions. Roger Penrose's Conformal Cyclic Cosmology proposes that the CMB may contain fossil signatures from a previous aeon. But the claimed Hawking point detections are contested, with reanalyses finding no statistically significant evidence after accounting for search procedures. Henri Poincaré formulated recurrence in dynamical systems in 1890. Bocchieri and Loinger proved the quantum version in 1957. Gary Gibbons and Stephen Hawking derived de sitter thermodynamics in 1977. Jacob Bekenstein proposed his entropy bound in 1981. Roger Penrose outlined Conformal Cyclic Cosmology in 2006. The Hawking points claim was published in 2018. The critical reanalyses followed in 2020 and 2024. The 2025 CCC refinement acknowledges tensions while continuing theory development. The investigation continues. The evidence accumulates. The conditionals remain. Finite information. Incomprehensible numbers of states. recurrence times longer than any duration we can conceptualize, e to the 10 to the 122 Planck times. And the conditional possibility, not the established fact that you have been here before. Not settled, not refuted, conditional. And we find ourselves here, brief, small, observing the cosmic microwave background with instruments that measure temperature variations of 1 part in 100,000, reaching across 13.8 billion years of cosmic history with equations and microwave receivers. Uncertain whether the light from before recombination contains messages from before the Big Bang. Uncertain whether recurrence theorems apply to a universe whose quantum gravity we do not understand. Uncertain whether time extends long enough for recurrence timescales to be reached. Uncertain what you means when asking whether a specific atomic configuration recurs after durations that cannot be written or conceived. The Bekenstein Bound says information is finite. The Quantum Recurrence Theorem says finite systems return. The de Sitter entropy says horizons have finite capacity. The Hawking point claim says evidence exists, but the reanalyses say the significance collapses under scrutiny. The chain of logic is valid. The premises are conditional. The claim is not proven. And we are left with a question, not an answer. A conditional, not a fact. A possibility that depends on assumptions. Physics has not settled and may never settle. You have lived this exact life trillions of times before. If information is finite, if states are finite, if time is infinite, if dynamics are suitable, if your configuration recurs, if identity is preserved across recurrence. Each if is a condition. Each condition has support. Each condition has uncertainty. This is what the data shows. This is what the data does not show. The investigation remains open. Good night.